After verifying the fundamental theorem for gradient, let us move on to the fundamental theorem for divergence, also known as the Gauss law or Gauss divergence theorem. In case of divergence, it is if we consider the divergence of a vector field V, and if we perform a volume integral of it, here V is for volume, and we will write the volume element as d tau as we have done earlier. That is nothing but a closed surface integral of V dot dA. What do we mean by closed surface integral in this context? So, we are in the left hand side, we are talking about a volume, and this is in the right hand side, this surface S is the surface that encloses exactly this volume, nothing else. We are talking about that surface in the right hand side. So, this is also known as I mentioned earlier, Gauss theorem. Again, we will not prove this theorem here, but we will consider an example by which we can verify this theorem. Let us consider a function V, a vector field that is given as y squared x cap plus 2x y plus z squared y cap plus 2y z z cap. And let us consider a cube with one of its corner at the origin. Here is our cube. And the axes are labeled this way. This is x axis, this is y axis, and this, although my drawing is not good, these axes are orthogonal, and the last one is z axis. The arm length of this cube is unit 1, 1 and 1. Now, we have to verify this we have to verify the divergence theorem with this example. Let us consider the volume integral first. So, we have to calculate the divergence of V for that. Let us calculate the divergence of V, that is twice of x plus y. You can do it and check for yourself. And the volume element d tau is given as dx, dy, dz. So, the volume integral becomes integration over the volume twice of x plus y d tau equals twice of all our variables are independent here, x, y and z, they do not depend on each other, and all three have the range from 0 to 1. So, we can write this integral this way. And if we work it out, then it becomes, we can independently work it out because these variables do not depend on each other. And if we try to independently work it out, we can find that the integral over x equals 0 to 1 x plus y dx is half plus y. Similarly, integral over y equals 0 to 1 we have here 1 plus y dy equals 1, and the last integral z equals 0 to 1, we will have to integrate over 1 dz, that gives us 1. So, what did we do? We have first performed the integral over dx, the range was from 0 to 1, and after performing that integral, we got half plus y, and then we performed the integral over y. So, there once we performed the integral, we got the result as 1, and then after performing this, we are left with the integral over z, and we performed the integral to get again only 1. So, that means we have evaluated the volume integral of the divergence of this vector field V, and that becomes 2 because we had a 2 factor in front. So, this quantity becomes 2. In order to perform the surface integral, we have to mark the surfaces. So, let us go back to this picture. Let us consider the front surface to be surface 1, front is surface 1, back is surface 2, surface 3 is this one, this side is surface 4, 5 is above, and 6 is below. We consider these to be the surfaces. Now, let us try performing the surface integral. On surface 1, we will have integral V dot dA. This is given as, so on surface 1, dx is not a variable, x is constant. So, dy and dz would be the variables. It is integral over 0 to 1, integral over 0 to 1 y square dy dz, because the direction is along x. So, we will only have the x component of the vector surviving here, the other components would not come, as we will take a dot product with the area element, and this will become 1 over 3, you can find it. On surface 2, we will have integration over v dot dA, and that is minus integral 0 to 1 integral 0 to 1 y square dy dz, just because we have the direction of this surface element in the opposite sense. We always consider the direction of a surface outside the box, and because these surfaces are opposite, we have different direction, and given the value of y, we will find that this is nothing but minus 1 over 3. Now, let us come to surface 3. Here integral over v dot dA, this becomes integral from 0 to 1, integral from 0 to 1, 2x plus z squared dx dz. Here the surface was along y direction, so y component of the vector comes in, and that becomes 4 over 3. Surface 4, let us consider integral v dot dA equals minus 0 to 1, 0 to 1, minus sign once again for the opposite sense of the direction of this surface, and here it is z square dx dz. That becomes minus 1 over 3. On surface 4, as we can see that x equals 0. So, we instead of 2x plus z square, we only have z square, and this is the value. On surface 5, we have v dot dA, that gives us integration over 0 to 1, integration over 0 to 1, 2y dx dy, and that becomes 1. On surface 6, we have integration over v dot dA equals again a minus sign, 0 to 1, 0 to 1, two integrals, and because on surface 6 we can see y equals 0 here. So, we will have 0 dx dy, so the contribution from here will be 0. Now, if we add up the contribution from all the surfaces, we can write down closed integral over the cubic surface v dot dA is 1 over 3 minus 1 over 3 plus 4 over 3 minus 1 over 3 plus 1 plus 0 equals 2, and the value from the volume integral was exactly 2. So, that means the theorem stands verified. The divergence theorem is verified.